Everyone, my name is Finil from Stevens Institute Technology, and very honored to chair this regular presentation. So let's welcome the first speaker, and her presentation title is Self-Healing Digital Twins, Hybrid Generative and Private Preserving AI for Adaptive Wellness Platforms. Thank you. Please come to the stage. You use this one to advance, okay?
Perfect. Which one? This
one to advance. Okay.
Hello. So hi, my name is Salma Atran. I have a master's degree in computer science, and I'm also a registered holistic nutritionist. So in this paper, I'm showing how I combine my nutrition background with my engineering background and created a very nice application that helping thousands of people to change their lifestyle. Also, my co-author is Nariman Mani. He has a PhD in computer engineering, and we did this presentation with this article together. So I am also the CEO of NutroSal. NutroSal is a company in which people register, they start to do great habits to change their lifestyle and especially lose weight. So we noticed in most of the application, the problem people have is they start, for example, they start a weight loss journey, but they stop it after a few weeks or few months. The main reason is they don't have a motivation. They really needed to have some sort of support. So this application that we created is based on groups. So people are in groups, and each group has a coach. But we injected artificial intelligence into the application to give feedback to users so they can stick on the plan more and more. So what we propose here, a self-healing digital twin framework, which is it integrates generative AI, reinforcement learning, and privacy preserving AI. So what this means is, as user registers in our application, we create a digital twin for that user, and what we do is, whatever happens to that user in terms of what they eat, what they drink, how much they sleep, we inject the data to that digital twin. And as they do the feedback, because they need to give us a report, and I'm going to show you here some of our screenshot of the application. So as you can see, user report in our application, all during the day, what they have eaten or how much water they had, how many hours they had sleep, and what time they went to bed, how much activity they had, what kind of workout, also the bowel movement if they had any, because all of this information give us a feedback that how that user is doing. So we have AI to capture the screenshot of the images, for example, to make sure what they're eating exactly is in the high quality, good habits of healthy eating. The other thing is that they can see, for example, the progress of their sleep, their water. They can also have some competition between the users by seeing who did this better and get motivated. And we have different groups. For example, in different groups, we show how much they lost weight, because that's the main factor. Because this is basically not only a healthy living or eating healthy application, but also it's very important for them to lose weight. So that's why we show them in each group how much they lost weight in that specific period. And they can see all their group mates to see how they're exactly doing in terms of scores, BMI, and so on. So what we did, we sent a survey to all of our clients, so about 3,000 clients, and we asked them the challenges they had in their past diets, because Many of them had different weight loss programs, plans before, but most of the time they couldn't get to the point that they wanted, and they couldn't maintain their weight. So 50% said we missed peer community support. So that's something that we're giving that in this application. 18% couldn't maintain and they get back to the old habits. And 15% face psychological barriers, like, for example, disordered eating, and 15% lack of mentorship. So we had mentorship in our application, and we had the community support, but with injecting AI and creating reinforcement learning, we started to learn about users, and based on the information that we are learning, we are basically giving information to user how they can do it better. As an example, for example, a user may not have bowel movement for 3 days. So in the old days, we used to say, okay, did you drink enough water, or did you have enough fiber? But right now, the AI captures everything in real time. They can see how much fiber they have, how much water they drank, and based on that specific needs that that user has, gives her information or suggestion what you have to do to fix this problem. So we are using hybrid generative and real reinforcement learning based on digital twins. That digital twin for each individual client exists, and we inject the data to that. And we also provided privacy preserving AI, because this is so important. This information is really critical for user. For example, their weight, their height, their body images. So that's why this information is really important. So that's why the privacy is another aspect of this article that we take care of. So if we go to this section, you'll see we are using dual cloud base, and I'm going to explain to you in the next slides how. But in here, in the first cloud, we take care of privacy, and in the second one, we are learning about the user, and we are giving the information to the user. So this is an example of a feature vector. For example, the user with this ID has high level of steps, normal heart range, the sleep category is in moderate, and these information has a score in our system. So, and that scores will be used to give suggestion to our, basically our clients. So as we see here, in our first cloud environment, what we do, we basically collect the data that we need regarding, for example, bowel movement, the water, the images of the photos, what they exactly eaten, and then we make sure we make them anonymous. And we do the anonymization, and we make sure that no information, no privacy information exists in that information, and then we inject it to the second cloud. In the second cloud, we start doing adaptive digital twin engine. And based on the information, we find any issue that that user may have, and based on the information that we have and the artificial intelligence has, we do add to our reinforcement learning, and we keep updating that. For example, for one user, maybe just an example, one user, water is the issue of constipation. For the other user, might be the fiber. For another user, might be sleep, because if somebody doesn't sleep enough, all the hormones gets disrupted. So we collect those information, and based on this information, we keep changing the personalized information, and we inject it to the data. And that means that the user will receive information about what they need to do to fix their issue. But the result that they're seeing as a, like, for example, the coach tell them you have to drink more water or you have to do that. This result shows very specific to that user. It's not really generalized, because the AI help us to make that specific for that user. Okay, and so I'm gonna do it fast. After deploying this, we noticed 26% started to stay in the plan more. which means less drop from the plan, or 14% less dropout, 25% more engagement. For example, in the beginning, people used to do a lot of engagement, but at the end of the plan, they started not to do anything. But with this plan, they started to continue until the end because they were thinking really the engine and the app is caring about their progress. So really, to conclude, we need to say this framework delivers adaptive, secure, and engaging wellness support. It goes beyond static AI by learning continuously, because it's not just some artificial intelligence that gives some static results to the user. It keeps learning and gives data to user. And yeah, we also we have planned to expand this to more users and add more features to it, and that's it.
Okay, thank you for the great presentation and a very
Thank you.
insight, and also clear pathway to clinical applications. So, any question from audience? Very quick question. So maybe I can ask a quick question. So can you elaborate more details on how the digital twin is built?
The twin?
Yeah, the digital twin, like do you use some deep learning model or use some regression method?
So what they do, for example, we collect all the information about the user, height, weight, for example, how much they drink, what they eat, and we create a digital twin exactly like that user, that we know, for example, this user is used to do these habits, all those sort of things. And then based on when the new data comes, the loop of new data comes, we inject the data again and we change that digital twin as it goes.
Okay, great. Thank you. Let's thank the speaker again. Thank you.
Thank you.
Okay. Our second speaker, so the presentation title is Generative AI for Smart, a leapfrog latent consistent model for medical image generation. Thank you. The floor is yours. Oh, sorry, yes.
Good afternoon, everyone. My name is Lakshmikar. I'm a PhD student here at Yeshiva University. So thank you very much for providing me this opportunity to present our research on a leapfrog latent consistency model for medical images generation. So along with me, the other collaborators who helped me in this work are Kalyan, Shenhan, Deepshika, Shilpa, Jalu, and Yushan Zhang. Dr. Yushan Zhang was our advisor for this work. So now let us discuss about this research, what we have done, and with what problems we have started. So here I would like to talk about two problem statements. So one is the scarcity of medical images poses a significant obstacle in effectively training deep learning models for medical diagnostics. This issue stems from the hesitance of the healthcare institutions to share their data due to privacy concerns and other regulatory constraints. And this medical domain lacks extensive data sets like ImageNet or Lion5B. Those data sets are relatively normally used for artistic images. That's why the models perform very better in those image classification tasks and other like artistic works of images. That is one problem statement that we have in case of medical domain. The other problem is normally we use diffusion models which shows superior performance in generating good images across all types of images. But the problem with them is they typically require 10 or more inference steps, which means 10 or more function evaluations, which means more time they take for generating images. And this generation of images started with GANs initially and then overpowered by diffusion models. Both GANs and diffusion models were applied in medical image synthesis, but they were applied only to a few disease classes. like at most 3 classes, like mostly 1 disease or 2 disease or at most 3 diseases, but they haven't been applied to multiple diseases across humans and animals. So to address these problems, we came up with 2 key contributions. For the first problem, we proposed a new dataset, MedImages dataset. It is a diverse and comprehensive collection of medical images that include both human and animal subjects covering a wide range of diseases. In the later part of the presentation, we will discuss about the dataset size and all. So this is in response to the problem that we faced, that we have discussed here in the earlier slides. So there is no huge data set similar to ImageNet and Line database. For that, we have developed this MedImages dataset. And to address the other problem with the long, like more inference steps required by the diffusion models to generate images, we introduced LLCM model, which utilizes the leapfrog solver. It is an efficient and rapid PF ODE solver. This is probability flow, ordinary differential equation solver. We have used it to generate high resolution images in as low as 1 to 4 inference steps, whereas with the diffusion models, we require at least 10 inference steps. That means 10 iterations we need, but whereas in our case, we require only a maximum of 4 inference steps to generate good quality images. So because of this, we trained our LLCM model on the wider medical images dataset that we have developed. Because of that, our LLCM acts as a vision foundation model across 159 disease classes of both humans and animals. So coming to our dataset, this is MedImages is the dataset that we created. It contains a total of 181K plus train images with 159 classes and 69K test images with 35 classes. So my collaborators helped me in collecting this data from the various online platforms like GitHub, Kaggle, and RoboFlow Universe. Initially, we collected 78 disease types with multiple classes, but the data was not clean, and we have some corrupted images as well. We spent a lot of time in cleaning the data and formatting the data. After cleaning it, the 78 disease categories were reduced to 61 categories. Finally, those are the different types of disease categories that appeared in our data set. And for the training, since we have a lot of different varieties of classes and images, so we limited each class to 2,000 images to prevent bias while training the model. And we reserved the excessive images for the testing. So once we cleaned all the data in terms of images, then we developed unique textual descriptions for each image, which serves as the input for our LLCM model. Image coupled with the textual description describing the disease of the image. Some examples are shown here, like image of benign acute lymphoblastic leukemia in humans and image of brain cancer. This is how we labeled each image, and we passed text and image to our model. And you can find more details about our dataset in our GitHub page. So to start our research, we built it on top of the diffusion models and consistency models. The diffusion models, they generate data by progressively adding the Gaussian noise to transform the data into pure noise, like shown in the figure here. We take a clean image and then we slowly add noise by means of scheduling so that the original image will be completely transformed to noise. And then there is a reverse denoising or reverse diffusion process where we will remove the noise to get the original or like a clean image without the noise. This is how diffusion models work. And then consistency models, they enable fast one-step generation by directly mapping the noise to the data, initial data, while still allowing the multi-step sampling to balance both compute efficiency and sample quality. So these are the two baselines we have used for developing our LLCM model. So coming to the methodology that we have followed. So the figure here shows the pipeline of medical image generation. So it starts with the images in the pixel space, coupled with input text that we have developed while developing the data set. And then we convert those images and the input text to the latent space from encoder to using image encoder and text encoder. And latent space images and text encoders are passed to stable diffusion model. So that is the base model that we have used. And we train the stable diffusion model and we save those weights, and those weights will be used by our LLCM model. And we use consistency model for the distillation loss to have like a one-step generation. So while solving from consistency model to the one-step generation, we use our leapfrog solver here. So this is the leapfrog solver. It is a numerical ODE solver like other ODE solvers. But here it's very rapid. Why? Because we calculate the midpoint velocity and then we add that to the earlier position of the, like if you say x1 is the particle position, initial particle position, and velocity is the midpoint, we get x2 by adding this velocity to the earlier midpoint. That is how we have applied the leapfrog solver. When we say x is the image and then velocity is the noise that we predict from there, then we add this noise in interleaved points like midpoints to get the original image. So this is how the leapfrog works. We have to assume the initial values for the image and the noise based on DDIM paper. So here we show the results. In the results section, here we have shown the type of hardware that we used. Like we have used A100 80 GB 4 GPU, 8 GPUs. And we trained it for 55 epochs with 184 batches and 28 samples per device. Essentially, it came around 1024 batch size. And we trained it for 10,000 iterations, and it took only 24 hours for complete training of this whole data set for our LLCM model. Here you see the sample of images that we show here, like original images in the first column. And the second column, you see the images that were generated after first iteration. And then we have shown the images for second, fourth, 8th, and 20th iteration. And we observe the images generated after fourth iteration. The quality is very good. And more images, you can find them on our GitHub page. And to measure the qualitatively, we have seen these kind of images, and to measure them, the quality, and in terms of quantitatively, there is a metric called FID. We use that FID metric, and we have compared other state-of-the-art models along with our model. And the lower is the score, the better is the model performance. I mean, the better is the quality of the images. So this is how we generate the images. And this one we have seen, like we have demonstrated on unseen dog heart dataset, we have generated images using our LLCM model. And here, after generating the images, actually the plan is to use those generated images in the original dataset when the dataset is small. So here you see we have applied this on the breast ultrasound images dataset. When we applied this, added this newly generated images to the original train images, the accuracy has improved a lot. You see here like a plus 3.15 for the overall accuracy. So our model has shown like demonstrated very good performance in terms of downstream tasks after utilizing the generated images by augmenting the original data set. Yeah, that's all. Thank you. Any questions?
Thank you for the great presentation. Due to limited time,
Thank you.
We can have one quick question.
Hello.
Yeah.
Thank you for the presentation. So I saw some like results table. You were showing steps from step 1 to step 9, I guess, or can you go to the next slide, please? Yeah, so here I see that like in only steps 4 and 6, your method is like outperform. So did you just like calculate the trade-off between the time complexity and the stable diffusion's accuracy? And how do you claim that your method is indeed outperform in both the accuracy-wise and the time complexity-wise?
Yes, so when the number of steps is less, it means it's taking less function evaluations, it means less number of iterations, so it means less time, okay? And coming to the quality, the lower is the score, the better is the quality. So FID score is lower at step 4. So if you compare the other state of the models like Stable Diffusion, Dream both, step 20 is, they have got the lowest values at step 20. Yeah.
Okay, let's thank the speaker again.
Thank you.
Let's welcome the third speaker for the research entitled Topology of Aware Conditional Latent Diffusion for Multi-View Fundus Image Synthesis.
Okay.
Use this to advance your slides, okay?
Oh, okay. Hello, everyone. My name is Gözde Demirci. Today, I will talk about our project about multiple view image synthesis. So first, I would like to introduce the clinical challenges we are having problem. So we are dealing with retinopathy of prematurity disease, which is a leading cause of blindness in preterm infants. And this RP disease has multiple stages. And through understanding the early diagnosis and early treatment, medical doctors, pediatric ophthalmologists need multiple field of view of the same eye so that they can understand the whole concept of the retina. For this, they need to take multiple pictures of the same eye, same patient at the same time, in the same time. So this behavior, unfortunately, taking repeated imaging risks discomfort for preterm infants as expected, and also it has really high time complexity as taking those pictures requires very professional pediatric ophthalmologists or clinicians. So to reduce this number of multiple view information, but keeping the diagnosis accurate, we try to use artificial intelligence or generative models to synthesize very accurate and structurally similar field of views. So when we talk about field of views, you can see the 5 examples here. These are all fundus images, retinal images with a different looking parts. So these are all the eyes, but they need to change the views for a specific angle. It's not random. So the problem arises when we use generative AI. Within generative AI with conditional, let's say, latent diffusion model or common latent diffusion model, even though they create really realistic images, unfortunately, they cannot preserve patient-specific anatomical structure, meaning that even though the color saturation and the contrast in the generated image, which you can see as an example of the third image, which is the latent diffusion model's result, is color-wise is really realistic, but unfortunately, it doesn't preserve the anatomical structure of the patient. So the first image you see is the condition image, which is the real image from preterm infant. And what we want to see is that if we see some branches on vessels, we need to follow those vessel layouts of the patient throughout the other field of views, because those branches or those vessel numbers or the tortuosity should not lost. So within this problem, within generative AI, we introduce a solution by using topology and called topology-aware latent diffusion model. So we basically use conditional latent diffusion model as expected. As a condition, we give 2 information, one real image, real preterm infant's image, and the other one is text input where we explain what kind of image we give and what kind of field of view, different view we are expecting. And with an output, we are expecting those desired field of view while we preserve the anatomical structure of the patient. As a key innovation, We use output level topology loss, and we are expecting this topology loss will help us to help the system to guide the preserved anatomical structure, as Sam said before, during the view synthesis. So how we use topology? Basically, topology is one of the mathematical concepts we use. It checks for structures of the object. Instead of a pixel-wise information, it extracts more like structural concepts. And in our study, we use 3 steps throughout the topology loss. First, we generate the image, and then we use preterm segmentation model to create the likelihood mask, so that throughout this likelihood map, we can generate what we call persistence diagram, which shows how many structures and what kind of important structures throughout this likelihood mask we have. So this persistence diagram is actually what we count, how many structures, how many like loops or cycles we have throughout the object. And each dots you see in the scatter plot is actually one persistence value that checks for that specific structure's birth time, where we start seeing, throughout the death time, where we stop seeing, either for complete loss of that structure or connected to other structures. So each persistence value here is actually mapping to towards the likelihood map. So as an example, for this red dot, red persistence value is actually mapping to that small vessel we see that is connected to main vessel, main artery vessel. So after seeing this vessel, we can use the filtration in our case, we are using sub-level filtration to understand throughout the thresholding, we see that specific vessel is indeed, growing. And then at the end, it's just like connecting with the structure. So the reason we use this approach and seeing structure-wise information is because we are not losing information here, and also we are discarding with like very small hallucination vessels that is not supposed to be there, practically in false positives, because usually pixel-wise approaches unfortunately extract those false positives into the loss as well. So after extracting topology loss by persistence diagram, we basically compare between the real image of the field of image and the generated image, and create those persistence diagram and then compare. So what we expect is that within this comparison, like consistency loss, we try to reduce the disagreement of the structure information, structure number, and basically topology. So we validated our approach by using a multi-view RRP fundus dataset within our collaborator of Changgung Memorial Hospital in Taiwan. So our main task is basically saying that generating nasal or temporal, 2 different field of views by using only optic disc center view. And as a metrics, we use image quality metrics, which is much more common metrics that is used in generative AI, generative models, as well as we use structural correctedness, which is Betty error, specifically checking for the topological correctedness. And as a baseline, we use latent diffusion model, 2 different variation, class condition and text condition. And we also use Pixopix to see other generative models, such as generative adversary network is also comparable in this study. So when we check for the quantitative results, we see that our model is outperformed in all evaluation metrics, including Betty error as expected. And when we check for the qualitative results, we see that the whole baseline is preserving the really good structural information in terms of color and tissue information. But beneath the tissue, the vessel segmentation is very well created within our approach with the help of topology. So within this approach, we can clearly see that the topological structure is indeed preserved by using the topology loss. So as a conclusion, synthesizing anatomical correct novel view is really important in RP studies, as well as the other studies as well. But within this, we are trying to improve the early diagnosis while we are reducing the traumatizing experiences within preterm infants. And we do see that our topology-aware diffusion model is indeed helping these like diagnosis, because after this extended abstract within our future studies, we see that diagnosis is also like improved within this approach. And within our method, we see that our method is like generating higher quality structural consistency images while comparing the other baselines. So thank you so much for your time. And if you do have questions, please let me know.
Thank you for the great presentation.
Thank you.
Given limited time, we have one quick question maybe from audience.
Yeah, hi.
Hello.
Thanks for your talk. So I have a question related to like the mask and the persistent diagram. So why didn't you generate the persistent diagram directly from the image? Why have you generated this mask in between?
Yeah, so within topology, we actually had to have like binary mask between 0 and 1 to understand what is the highest point, which is 1, which is the vessel, and what is the lowest point, which is 0. So while we introduce RGB channel, like three-channel fundus images, there are so many noises that we don't want to focus on. So that's why we introduce vessel segmentation here. Oh yeah, definitely. But actually so basically what we had to do is that we have to get rid of the GPU and calculate everything on CPU. This is the reason there is some time complexity. But within this data set, we actually trained the model within only 1.5 days with 3,000 images, which was like, when it comes to topology, I guess it's pretty good trade-off when we see the results. Yeah.
Okay, great. Let's thank the speaker again.
Yeah. Thank you.
So now let's welcome the fourth speaker. For the research entitled Approximate Knowledge Graphs, Privacy Preserving Healthcare Data Synthesis via LLM-Driven Approximation.
Hello, everyone. I'm Shenglin Li. I'm a postdoc researcher, work at the AI Center from University of Alabama. It's a very honored to present our research today, and although it's at a very beginning phase. So today's I'm gonna present the approximate knowledge graphs. This is the contents of today. So the motivation of this research, we know the healthcare data sharing is very important. It facilitates large-scale clinical research and also support collaborative medical research across institutions and like hospital, the school, and between the peoples. But however, for privacy regulations limit data use, like HPA and GDPR imposed strict rules regarding the sharing of patient data. So it's like direct share of the real data, like EHR data, is often infeasible, impossible. So there is need for alternative methods that enable research without exposing the sensitive data. The limitation of existing data protection methods. The first is noise-based, the approximation method, which provide strong privacy guarantees, but severely degrade data quality. The second is realism-focused generative methods, which produce the data that looks high realistic, but often risk memorization leakage. So it seems like it's really hard or to find a way to anonymize the instruct task or the data without losing clinical information. So that's this research objectives. The first, the balance data utility and the privacy. The second, we want to use, right, like integrating the large language model capabilities into the knowledge graphs. We want to leverage the capability of large language model to extract the detail from the raw data, and the used the structured representation in knowledge graphs to ensure or to show the data coherence, interpretability, and clinical accuracy. The final result, the final goal is produce the clinically valuable synthetic data. So our proposed methodology includes three types, the three steps. The first is structured knowledge graph construction from the raw data use large language model. The second is build a balance controller with parameters from 1 to 10 to guide privacy management. And the final step is the knowledge graph abstraction to anonymize sensitive detail and preserved essential information. This is the workflow of the proposed methodology. The data for this research, we used the raw data, the EHR data in CSV format. Each row is the patient, and each column is the feature. And we use large language model to process the data to get structured data. It's like to predict the relation between the features. And based on the structured data from the large language model, we can have a comprehensive knowledge graph. And the knowledge graph, and the comprehensive knowledge graph will pass the controller, the balance controller. So the 10 with the number from 1 to 10. The 10 means we focus on the utility, extremely focus on the utility. That means we use raw data. And the parameter 1 means we extremely focus on the privacy. So we just protect the patient information. So it's just totally blur the number. So after that, we get approximation knowledge graph. The evaluation data set in this research, we use 20,000 patients with cancer diagnosis, include features like age, tumor size, tumor type, treatment response, and survival status. The linear classification test is pretty simple. Just you predict tumor type using the age and the tumor size. And we evaluate the approximate results between the privacy and utility in classification accuracy for each parameter. So this is the result of the anonymized patient data. So the parameter 10 means we focus on the raw data. So it's the we focus on the utility. That means the raw data, right? We can see the age and the tumor size. And the parameter is 1. It means we extremely emphasize on the privacy. So that's totally blurred. There's no value can show. It's just a task to describe. And from the 9 to 2 is just represent the approximation level from less to more. This is the result between the comprehensive kg and approximate kg. The up one, the top one is the comprehensive kg. So it's from the large language model. So large language model predict the relation between the nodes, and each node have the property with the value. And through the balance controller, we have the blurred. If you choose the parameters 1 is totally blurred, just show in the approximate kg. This is the result of the privacy and the utility. So first, look at the parameter 10. The parameter 10 is raw data. So the baseline, the utility accuracy is around 60. And because we use raw data, so it's 100% re-identified accuracy, right? That means it definitely can find the raw patient. So, but if you focus on the parameters 1, that's totally blurred. There's no way to find raw data. But also the utility accuracy is 0. So that's not what we want. So if we check the parameter 7, 8, 9, we just sacrificed a little bit the utility or the downstream task accuracy, but we can reduce the re-identification accuracy very much. That's what we want. The conclusion, so our method offers a practical method for balancing the data privacy and utility. And the parameterized approach offers flexibility for various downstream tasks. The future work, there's a 2 points in the future works. The first one, we just use very simple and kind of structured raw data in CSV format. And in the future, we definitely will incorporate the diverse data sets, like totally unstructured and Dr. No's comments from the HR data sets. The second is refine the approximation strategies, like use larger language model to automatically detect the required privacy level based on the downstream, the task model, or on the context. Thank you. Any questions?
Okay, in a very limited time, if you have questions, please ask Dr. Lee or mine.
Okay.
Let's welcome the 5th speaker. Okay. For the research entitled "Extracting Causal Relation Rules for Medical Question and Answering Tasks Using Large Language Model." Yeah, you are using your own. I don't know how to set. I don't know how to set this up. I think you will be fine. This is kind of late. Let me ask Dr. Guo. The speaker want to use his own slides. The speaker want to use his own slides. Yeah, but he has a new word. This has no notes. It doesn't have the notes. Yeah.
Okay, that should be fine. Don't worry. Just be easy. Yeah, thank you.
Hello, everyone. Thank you for giving me the opportunity to talk here. So it's not showing.
Oh.
Okay, thank you. Okay. So on the behalf of our authors, myself and Nisona Roman, will talk about extracting causal relational rules for medical question answering task using large language model. We know LLM have shown strong capabilities in understanding, summarizing, and answering general QA. In sensitive domain like medical, an open source model can have great accuracy if it is fine-tuned or trained on medical data. But the problem is still persist. That's the hallucination. So rather than the knowledge gap, the model hallucinates mostly because of the messy descriptions. It often includes the complex medical terminologies and the clues that needs a reasoning to understand the question. So can we help LLM to understand the question better? And the answer is yes. If we provide refined summary that shows the connection between the symptoms or the diagnosis reports, it can help to understand the question better. But the problem is we lack of structured causal graph or knowledge. So in this study, we proposed a prompt-based framework to extract such refined summary that can help for the downstream task. So let's start with an example. So in this example, the question asks, what the most likely cause of the patient disorder? The answer is shown in the highlighted green color. And our main goal is to extract this rule. If you pay attention, this rule actually have successfully has the connection between the question and the answer. So our goal is to extract this rule. But while doing so, we face few challenges. Like I told you, like the question is very messy. It has free form, like it has no consistent structure. It often includes jargons, lab reports or something. Secondly, it needs causal reasoning capabilities to summarize this question with and connecting with the answer. So we used like large language models like GPT's capability to summarize this question and connecting the causal relations between the question and the answer. So let me give you the framework so we designed. Like I told you, it's the prompt-based engineering. So first in the prompt, we frame the GPT model as a medical expert so that it can expect what task it's going to do. Then we just give the demonstration, we instruct the model to how to reason the question first, then how it can generate the rule using the correct answer. And for demonstration, we also provided a 3x here to reasoning example for having the consistent result. So first, when the model generated rule, we check if the rule actually included the correct answer or not. Based on this, if it includes the correct options in the rule, then we'd finalize it as a final rule. If it's not, otherwise we're going to the second steps. That's like a self-judgment, we're calling it self-judgment, because after providing the causal rule itself and with the correct reasoning, GPT can revise its own generated rule. So based on this, like, is it the valid rule or isn't it not? So based on this, GPT may refine its rule. Again, we finalize as the finalized rule. And to facilitate this extraction, we also define some types of causal rules. So like here, we define 3 types of causal rules. The first one, in terms of the difficulty or the chain of rule, how long it is. So the L1 rule is the simplest one, that cause and effect, like smoking causes cancer. Most of the works, recent works or existing work, actually extract the causal rule like this form, like triplet, cause and effect triplet. So then we have the L2 that includes one more step reasoning, like smoking causes cancer and cancer causes death. And we have the multi-reasoning, the L3, and it is flexible, like multiple contributing factors can cause any one cause or one effect. Here an example of L2 rule, like the highlighted with orange color can represent the nodes as the cause and effect, and it also shows how they're related to each other. And this rule can be formatted as a knowledge graph. So let's talk about how the self-judgment enhancement work here. So for these questions, it asked what is the most appropriate disposition for the patient's situation. So while first our framework generated a rule, it was including the wrong answer, the wrong options, like highlighted with the orange color. So the idea was like without the instruction for extracting the rules, we just ask the GPT, okay, answer these questions with the CO2 reasoning, and it can answer the question correctly. So that led us to have the self-judgment enhancement, because GPT has the knowledge to answer correctly the question. So we are providing the COT of the correct answer, and to define the rules, it was generated earlier. And it can actually enhance the rule, it can enhance the rule with the correct options. For this, we used a Medhall dataset, and it consists of like a 19,000 key web pair to challenge LLMs to test on hallucinations. So our main goal was to test a Meerkat 8 billion version, a small model, to challenge how Meerkat have the reasoning capabilities to answer the question. So first we filtered with regex and keyword searching, and filtered out like 3,000 questions that may require causal reasoning to answer. And then we test these 3,000 questions on Meerkat to find out the 949 questions that it couldn't answer correctly. And we use these 949 questions to extract the causal relation so that we can test that how the causal summary can help to answer the question using the Meerkat model. And we use GPT-4o with different setting for the summarization of the question answer, like the 0 shot, 3 shot with COT or without COT, and at the end we use the self-judging. So here is the result of the rule extraction. This is a distribution of how many, the number of rules type it extracted, like the L1, L2, and L3. You can see that GPT with the 0 shot has like 99%, like the most of the thing, it's showing as a triplet, like cause and effect only. But if you pay attention while we're using the 3 shot examples and the COT, it's like an L2 from 0 to 25%. So it knows how to generate a more complex or reasoning rules here. While using the self-judging here, it's quite similar with the CO2 or 3 shot, but it enhances the correctness of the rules. So we are defining correctness as if the rule including the correct options in the rule, so that actually we are defining as a correct rule. As you can see, the 0 shot has like a 60% accuracy to make it correct, and while we're using the self-judgment, it is like a 70%. So obviously the self-judging actually helping to make it the correct rule. And we also had a human study, because the automatic can be fallible, this rule. Okay, thank you. So we also have the human study, and that shows that how the rule is reasonable to answer the questions, actually. So what are the takeaways from this study? Like extracting the multi-step reasoning rules, we can use the prompt engineering based, and these rules can be formatted as a knowledge graph later on to improve the downstream performance. And the quality of the rules actually consistent with the human study. And the self-judging is essential for the high-quality rules. And our ongoing works actually refining the rule extraction with different LLMs with various reasoning capabilities like R1 or O1 from GPT. And we're also designing an automatic evaluation using multiple LLM as NLI judges to evaluate the rules. And thank you. If you have any questions, I can answer.